I'm Mitch Stoberl, and this is the Embedded Systems DC motor lab running 5 interrupts, timer 1, just setting the period of the pulse width modulation, and then timer 1 comparing to set the pulse width modulation, and then timer 2 just interrupts every 10 milliseconds to keep track of time. And then interrupt is calculating it on the rising edge of the encoder, and then interrupt for the data to and from the PC. And then the LCD will be the data being sent to and from the PIC for part 4. Line 2 will be the desired speed, line 3 will be pulse width, and line 4 will be the speed. And there's the schematic, so you got the encoder 1 and 4 tied to power ground, and then RB0 is the encoder, and RC 6 and 7 are the sending receiving lines. RA0 is the 5K pot on the PIC board, and then just using a transistor as a switch to drive the motor. And for part 1, we are just going to be incrementing the pulse width from 0 to 100% and displaying to the PIC and the PC. And it takes a while for the motor to start. There it goes. And there were just my calculations for my practice for checking and setting the interrupts. And then there is the blue line for the actual increase of the motor with the pulse width. The red line is just a curve fit showing that motors aren't a linear device. It takes a while to overcome the friction and actually get the motor to start going, and it does not increase linearly, nor just keep going off to infinity. Alright, and for part 2, we will take the data from the curve fit from part 1 and create a speed function for the CCPR1, as you can see there in the code. As you can see, it starts up right away, more or less. And the reference is more or less the same as the speed. And then just again, the pulse width. And then writing to the screen again. Alright, and then here we have our black line is the ideal. Reference is equal to speed, what we want it to be. The curve fit is based off the real data of the motor increasing, so it's not bad, but it's not ideal. Alright, for part 3 we'll be using the potentiometer to set the speed, or the reference speed that we want it to go at, and if the actual speed is less than the set speed, the pick will increase the pulse width. If the speed is greater than the set speed, it will decrease the pulse width, and if they're both equal, it will hold whatever pulse width it takes to maintain that speed. And in the main program, that's just CCPR1 plus the quantity of the reference minus speed. So as you can see, we are going 0 and it's showing 0. So we increase, just say that's so we increase and the pulse width does indeed increase. And I'm using 12 volts just so we can make it go faster, a little nicer. And then when we decrease, it indeed goes down. And then we have our data recording again. Right, and then for part 4 we will be doing the same thing we did in part 3, only we will be using the keypad on the computer keyboard. And then that's the code to set it in the for the serial terminal and the collect the data. And we got our code recording again. So we're going at just slow speed, stable pulse width. Let's go 750. Enter the flag, and it sets the speed, which then increases the pulse width to match that speed. And using 12 volts again. And we bring it to a slow speed, and it does decrease to set that slower speed. And to stop. So here is what the graphs of 3 and 4 should look like. You set the reference and the speed will increase or decrease accordingly. So for part 3, the reference, which is blue, is a little not so square just because it's finicky to get where you want to set. But it does indeed increase and decrease accordingly. The PC or the keyboard is much cleaner because as soon as you hit enter, it goes to the set speed automatically, and the motor increases or decreases to match that speed. And that one right there is actually pretty much identical to the ideal plot.